Energy analysis of closed systems. This topic introduces energy analysis of closed systems, where the mass remains constant during the process. The main focus is how heat and work affect the change of energy inside the system. This concept forms the foundation for understanding the first law of thermodynamics in a practical way. The approach is always based on energy balance and thermodynamic properties. Mastering this part is essential before moving to flow system analysis.
Lesson Plan Thermodynamics 1. This section shows the position of this chapter within the overall structure of the Thermodynamics 1 course. The chapter sequence is designed so students build understanding from fundamentals to advanced applications. This chapter comes after pure substance properties and before control volume analysis. This means the focus is on applying the first law to fixed mass systems. This structure helps develop understanding in a gradual and systematic way.
Learning outcome. These learning outcomes describe the abilities expected after completing this chapter. Students should be able to analyze boundary work, the first law, and energy changes. In addition, the concept of specific heats and their applications are key targets. The ability to solve numerical problems for various substances is also emphasized. All of these aim to build a strong foundation for advanced thermodynamic analysis.
Boundary work concepts. Boundary work arises when the system boundary, such as a piston, moves due to internal pressure. This motion indicates an energy interaction between the system and the surroundings. In many machines, boundary work is the most important form of mechanical work. Gas expansion and compression are the most common examples of this phenomenon. Understanding this concept is essential before moving to the mathematical formulation of work.
Differential work by gas. The gas exerts a force on the piston and causes a small displacement of the system boundary. This small displacement produces an infinitesimal amount of differential work. The magnitude of this work depends on the gas pressure and the piston area. By accumulating these small works, the total work can be calculated. This concept is the basis for deriving the boundary work equation.
Boundary work on PV diagram. Boundary work can be visualized as the area under the curve on a PV diagram. Each process has a different path and therefore produces different work. A small area under the curve represents differential work. By integrating along the entire path, the total work of the process is obtained. This is why work strongly depends on the process path.
Check your understanding. Number 1. This question checks the understanding that the area under the curve on a PV diagram has a specific physical meaning. This concept is not just a graphical representation, but has a real energy interpretation. Students are expected to connect the graph with the concept of work. This understanding is essential to read and interpret thermodynamic diagrams. Without it, process analysis becomes incomplete.
Path-dependent boundary work. Boundary work is not determined only by the initial and final states, but also by the process path. Two processes with the same initial and final states can produce different amounts of work. This is shown by different paths on the PV diagram. Each path encloses a different area. This demonstrates that work is a path function, not a property.
Net work in a cycle. In a cycle, the net work is determined by the difference between work output and work input. Graphically, the net work is represented by the area enclosed on the PV diagram. The direction of the cycle determines the sign of the net work. If the cycle is clockwise, the system produces net work. This concept is very important in heat engine analysis.
Polytropic process insights. A polytropic process
follows a general relationship between pressure and volume with a certain index. The value of this index determines the shape of the process path on the PV diagram. By choosing different index values, many thermodynamic processes can be modeled. This process is very flexible and is often used in engineering analysis. Many real processes can be approximated using this polytropic model. Energy balance in cycles. In a thermodynamic cycle, the system returns to its initial state, so the net change in total energy is zero. As a consequence, the net heat input must be equal to the net work output. This relation represents the simplest form of the first law for cyclic systems. The closed loop on the PV diagram visually illustrates this energy exchange. This concept is the basis for understanding how heat engines and refrigeration machines work. Answer: B. Net heat input equals the net work output during a complete cycle. Explanation: A. The net energy change is non-zero since the system does not return to its initial state. This is incorrect, because in a thermodynamic cycle, the system returns to its initial state, meaning the net energy change is zero. B. Net heat input equals the net work output during a complete cycle. This is the correct answer, as in a thermodynamic cycle, the heat input to the system is converted into work output, assuming no losses, ideal cycle. C. The system's efficiency is always zero for a thermodynamic cycle. This is incorrect, because the efficiency of a thermodynamic cycle is not always zero. It depends on the specific cycle and the ratio of work output to heat input. D. The closed loop on the PV diagram represents the energy transfer efficiency of the surroundings. This is incorrect, because the closed loop on the PV diagram represents the energy transfer efficiency of the system, not the surroundings. First law for closed systems. The first law for closed systems states that energy entering as heat and work equals the change in system energy. For stationary systems, the energy change usually involves only internal energy. In differential form, this relation describes instantaneous changes in energy. This equation is the core of all energy analysis for closed systems. All special cases in this chapter are derived from this general equation.
Constant pressure process. In a constant pressure process, the combination of internal energy change and boundary work equals the change in enthalpy. This relation is very useful for analyzing piston-cylinder processes with a constant load. A quasi-equilibrium assumption is required so that pressure can be treated as constant. If pressure varies significantly, this relation no longer applies. Therefore, choosing the correct process model is very important. Expansion in vacuum. Expansion into a vacuum produces no work because there is no opposing pressure. Even though the system boundary moves, there is no force to overcome. As a result, the system energy change does not involve any work. If the energy changes, it must be due only to heat transfer. This process is often called free expansion. Heat capacity comparison. Each substance requires a different amount of energy to raise its temperature by the same amount. Water needs much more energy than iron for the same temperature change. This difference is caused by the different specific heat values of the substances. This example shows that not all materials respond to heating in the same way. This concept is very important in heat transfer calculations. Specific heat concept. Specific heat is defined as the energy required to raise the temperature of 1 kilogram of a substance by 1 degree. The higher the specific heat, the more energy is needed for the same temperature change. This concept directly links energy with temperature change. In engineering analysis, specific heat is often assumed constant over a certain temperature range.
This definition is the basis for all heating and cooling calculations.
Check your understanding. Number 3. This question tests the understanding of the basic definition of specific heat. The correct answer must match the formal definition given earlier. This is not just memorization, but understanding of its physical meaning. This concept will be used in almost all subsequent energy analyses. Therefore, a correct understanding is crucial.
Specific heat at constant conditions involves no boundary work, so all energy goes into increasing internal energy. In contrast, at constant pressure, part of the energy is used to do boundary work. Therefore, specific heat at constant pressure is always greater than at constant volume for gases. This difference reflects different mechanisms of energy storage and use. This concept is very important in ideal gas analysis.
Definitions of specific heats. Specific heat at constant volume is defined as the rate of change of internal energy with respect to temperature. Specific heat at constant pressure is defined as the rate of change of enthalpy with respect to temperature. These two definitions provide a more formal and mathematical meaning. With these definitions, energy changes can be calculated by integrating over temperature. This is the theoretical basis for using tables and specific heat equations. Specific heat variation. The value of specific heat is not always constant and generally increases with temperature. For higher temperature levels, more energy is required even for the same temperature rise. This phenomenon is clearly observed in air and other gases. Therefore, the assumption of constant specific heat must be used carefully. In more accurate calculations, this variation must be taken into account. Joule's experimental apparatus. Joule's experiment shows the relationship between work, heat, and internal energy change. High-pressure air expands into an evacuated chamber through a valve. The temperature change is observed using the surrounding water. This experiment proves that internal energy is a property. This result becomes an important foundation for the concept of internal energy in ideal gases.
Answer B. The water surrounding the chambers measures temperature changes, demonstrating the relationship between work, heat, and internal energy changes. Explanation. A. The compressed air expands into an evacuated chamber, but there is no change in temperature. This is incorrect because the temperature changes due to the expansion of air are measured by the surrounding water. B. The water surrounding the chambers measures temperature changes, demonstrating the relationship between work, heat, and internal energy changes. This is the correct answer. The temperature changes of the water reflect the energy transferred, which is related to work, heat, and internal energy changes. C. The compressed air does not expand into the chamber, and temperature changes are measured by the air itself. This is incorrect because the compressed air does expand into the chamber, and temperature changes are primarily measured by the surrounding water. D. The valve prevents the air from entering the chamber, so no energy transfer occurs. This is incorrect because the valve allows the compressed air to expand, enabling energy transfer and leading to temperature changes in the surrounding water. Ideal gas properties. For an ideal gas, internal energy and enthalpy depend only on temperature. This means that changes in pressure or volume do not directly affect the energy. The specific heats at constant pressure and constant volume are also functions of temperature only. This property greatly simplifies thermodynamic analysis. Therefore, the ideal gas model is very frequently used in engineering calculations.
Specific heat trends. In general, the specific heat at constant pressure increases with increasing temperature. Polyatomic gases, such as CO2 and H2O, show much larger variations. In contrast, monoatomic gases, such as argon and helium, have nearly constant values. This difference is related to molecular structure and internal energy modes. This graph helps in understanding the thermal behavior of different types of gases.
Ideal gas table basics. Ideal gas tables use 0K as the reference point for energy. The values of internal energy and enthalpy are then tabulated as functions of temperature. With these tables, energy changes can be obtained directly without performing integration. This approach is very practical for engineering calculations. Understanding how to read these tables is essential in thermodynamic analysis.
Specific heat approximation. For small temperature ranges, specific heat can be approximated as a linear function of temperature. With this approach, an average specific heat value is used. This method simplifies calculations without losing much accuracy. In many engineering cases, this approach is more than sufficient. However, for large temperature ranges, this approximation must be reconsidered.
Check your understanding. Number 5. This question emphasizes again an important assumption in the specific heat approximation. Students are expected to remember that this approach is valid only for small temperature ranges. The correct answer reflects an understanding of how specific heat varies with temperature. This concept is often used in practical calculation problems. Therefore, a proper understanding is necessary.
Internal energy relation. The change in internal energy depends only on the change in temperature, not on the type of process. This applies to both constant volume and constant pressure processes. This concept is a direct consequence of the ideal gas property. Therefore, the process path does not affect the internal energy change. This greatly simplifies many energy analyses. The change in internal energy can be calculated directly from property tables. In addition, the integration of specific heat over temperature can also be used. Another, simpler approach is to use the average specific heat. The choice of method depends on the level of accuracy required. All three methods are very important in practical thermodynamic analysis. Specific heat relations. For ideal gases, the specific heat at constant pressure can be derived from the specific heat at constant volume and the gas constant. This relation shows the fundamental connection between Cp, Cv, and R. Specific heat values can be expressed on a mass basis or a molar basis. The choice of basis depends on the needs of the analysis. This relation is very frequently used in gas thermodynamic calculations. Incompressible substances. For liquids and solids, the specific volume remains nearly constant during a process. The effects of pressure and temperature on their volume are usually very small. Therefore, these substances are often treated as incompressible. This assumption greatly simplifies energy analysis. This approach is sufficiently accurate for most engineering applications. Specific heat of incompressibles. The specific heats at constant volume and constant pressure are considered identical. Therefore, only one specific heat symbol, C, is usually used. This specific heat value is generally nearly constant with temperature. If there is any variation, it is usually small and often neglected. This simplification makes energy calculations much easier. Answer: A. Specific heats at constant volume and pressure are identical for incompressible substances. Explanation: A. Specific heats at constant volume and pressure are identical for incompressible substances. This is the correct answer because, for incompressible substances, the specific heats at constant volume and pressure are equal, which is a defining characteristic of such substances. B. Specific heat values are highly temperature dependent and vary significantly. This is incorrect because, for incompressible substances, the specific heat values are generally constant, with only slight temperature dependence. C.
Specific heat at constant volume is always larger than at constant pressure. This is incorrect because, for incompressible substances, the specific heat values are equal, not one being larger than the other. D. Specific heat values are only constant at high temperatures. This is incorrect because, for incompressible substances, the specific heat values are constant across a range of temperatures, not just at high temperatures.
References. This section shows the main sources of figures and concepts used in the material. The primary reference comes from the Thermodynamics textbook by Schengel, Bowles, and Kanoglu. This book is one of the international standard references in engineering thermodynamics. Using a strong reference ensures consistency of concepts and notation. It also makes it easier for students to study further from the same source.